Hello and welcome back to Engineering Mechanics lectures. In our last lecture, we determined the velocity of a point on a rigid body in plane motion by adding the relative velocity due to rotation about a convenient reference point with respect to the velocity of the reference point. In the first part of this lecture, we will solve the problem by choosing a unique reference point which momentarily has zero velocity in pure rotation about an instantaneous axis of zero velocity. This is called the instantaneous center of zero velocity. Now consider this figure. Assume we know the directions of the absolute velocities of any 2 points, say A and B, on the body that are not parallel. If there is a point about which A has absolute circular motion for the instant being considered, this point must lie on the normal to the velocity vector of A through A. Same is true for B. The intersection of the two perpendiculars is the center of rotation for this instant. And point C is the instantaneous center of zero velocity. So point C could lie on or off the rigid body. If we know the magnitude of the velocity of one of the points, say the velocity of A, we can compute the angular velocity omega, which will give us omega equals to velocity of A divided by the radius of A. And then we can compute the linear velocity of every point in the body. For example, the velocity of B will be equals to the RB multiplied by omega, which is equals to also RB, the ratio of RB and RA multiplied by V of A. If the velocities of 2 points in a body having plane motion are parallel, that is figure B and C, and the line joining the point is perpendicular to the direction of the velocities, the instantaneous center is located by direct proportion as shown in these figures. We can readily see from figure B, for example, that as the parallel velocities become equal in magnitude, the instantaneous center moves further away from the body and approaches infinity in the limit as the body stops rotating and starts to translate. The locus of the instantaneous centers in space is known as the space centroid, and the locus of the positions of the instantaneous centers on the body is known as the body centroid. At the instant considered, the two curves are tangent at the position of point C. It can be shown that the body centroid curve rolls on the space centroid curve during the motion of the body, as indicated schematically in figure 5.8. Now I will explain the solution of sample problem 511 in your textbook. The wheel in this figure rolls to the right without slipping, with its center O having a velocity of 3 meters per second. Locate the instantaneous center of zero velocity and use it to find the velocity of point A for the position indicated. So we know that for pure rolling, and when there is no slip, therefore there will be a zero velocity at the point of contact of the wheel with the ground due to pure rolling. Therefore the angular velocity of the wheel becomes omega is the velocity at point 0 divided by the distance OC. This will give us 3 divided by 0.3, which is 10 radians per second. So now we have the angular velocity for the body. And so to find the linear velocity of point A, we use the cosine rule to find AC. Hence, we compute the velocity to be AC multiplied by omega, which yields 4.36 meters per second. The direction of the velocity vector v of A is perpendicular to AC. In this second part of the lecture, we will consider the relative acceleration due to rotation. The relative acceleration equation is generated by differentiating the relative velocity equation. If we consider 2 points A and B in plane motion in terms of non-rotating axis, the velocity equation in vector form will be given by the velocity of A, which is equals to the velocity of B plus the velocity of A with respect to B. If we differentiate this equation with respect to time, we get the relative acceleration equation. Equation 5.7 states that the acceleration of point A equals the vector sum of acceleration of point B and the acceleration which A appears to have to a non-rotating observer moving with B. If point A and B are located on a rigid body in the same plane of motion, and the distance between them is r, and let's say r is constant, so that the observer in B will see A as having a circular motion about B. Since the relative motion is circular, the relative acceleration will have a normal component due to change in direction of the velocity of A with respect to B, and a tangential component due to the change in magnitude of velocity of A with respect to B. Therefore, we can write our acceleration of A, which is equals to the acceleration in vector form of B plus the acceleration of A with respect to B in the normal plus the acceleration of A with respect to B in the tangential. And the magnitude of the relative acceleration, which is A with respect to B tangential, will be equals to alpha r. Let us interpret the relative acceleration equation. The meaning of equation 5.8 and 5.9 is illustrated in figure 5.9, which shows a rigid body in plane motion with points A and B moving along separate curved paths with absolute accelerations A of A and acceleration of B. The figure shows the acceleration of A to be composed of two parts, the acceleration of B and the acceleration of A with respect to B. Alternatively, we may express the acceleration of B in terms of the acceleration of A, which puts the non-rotating reference axis on A rather than B. This order gives the acceleration of B will be equals to acceleration of A plus acceleration of B with respect to A. Here the acceleration of B with respect to A and its normal and tangential components are the negatives of the acceleration of A with respect to B and its normal and tangential components. Just as we did in the relative velocity method, we can find the solutions to equation 5.8 in three different ways: by a scalar, algebra, and geometry, or by vector algebra, or by graphical construction. Okay, I would like you to read solution of the relative acceleration equation. It's a paragraph on page 382 of the textbook, and solve problems 5/123 and 5/128 from your textbook. Thank you, and I will answer any questions you may have during our contact session, which I will announce on the MS Teams and WhatsApp group. Bye-bye.